And then we go to the last scientific contribution of this TISOLS, and maybe as prophecy, but we're going to Taiwan for this this contribution.
Yeah. Hello, everyone. My name is Pingtung. I'm a PhD candidate in the National Central University in Taiwan. So we belong to the geohydraulic research group. So today I will give the talk about land subsidence due to the groundwater extraction and tectonic activities in Pingtung Plain, Taiwan. Because the Pingtung Plain, Taiwan, they have a serious tectonic. Oh, not serious. They have the active tectonic in this area. So in this talk, I will give you about 5 parts. The first, introduction. The second, the background, where's the Pingtung located. And the next one, what kind of method I want to do to finish this research. And the next one, I will give you the results and discussion. And finally, I will draw the conclusions. In the introduction, here is the 2007. They have the authors, they observe the GPS deformation. They found that from the 10 years, 1995, 2005, they have a zero land subsidence in the coastal plain. They don't know why. So they have a zero land subsidence. We see that they have purple color, minus 30 millimeter per year. So the first, some authors point out the first due to maybe wet and dry season. This means due to the hydrogeological condition effect. The second one, groundwater over extraction. And the next one, also 75% of land subsidence here due to the over extraction of groundwater. And another tectonic subsidence associated with tectonic extrusion at the southern tip of the Taiwan collision belt here. This is the Taiwan collision belt in the central range. So this study provides an innovative idea by using the multiple geodetic technique to separate the shallow depth and the deep depth. Because in this both study, they combine together because that time they don't have the shallow monitoring land subsidence. But they just use the GPS or INSAT to do the observation and explain what is the mechanism of this. However, they don't exactly investigate the mechanism of land subsidence, maybe due to the groundwater extraction or not. They just observe that. However, in this study, we combine together to figure out the mechanism and also how much land subsidence induced due to the different mechanism. So this is the Pingtung Plain. We can see they have a serious land subsidence. This is sinking how it's sinking. We see they are serious. It's not one house. It's many houses. They subside. So what's the physical meaning? What's the mechanism of this area? So this is our purpose to stay here to talk with you. So in the background, here is the Pingtung Plain in the Taiwan. You can see the elevation range about 0 to 50 meters above mean sea level. And then we have the several monitoring here, including the GPS stations, land subsidence monitoring well, commonly we call it a multi-layer compaction monitoring well, and also groundwater observation. They locate together, and some parts they have a co-located. The co-located is very important because they can imply your mechanism, because the co-location is very important. So we well know in some authors on some presenters also point out that the total subsidence can be measured by the GPS leveling, also the INSAT technique, because they measure in the ground surface. The next one, also a device developed in Taiwan. They call it a multi-layer compaction monitoring well. They can measure the compaction in the various depths. For example, they can have the 10 meter, 20 meter, 50 meter, 100 meter, 200 meter. They can have a different. And next one, groundwater observation. So we need to have this to know what is the correlation between them. So what is the disadvantage and advantage of each sensor? The first leveling, we have very high accuracy, about vertical accuracy about 0.5 to 1 centimeter. In the continuous GPS, we have the 1 day for the fluency. In the MLCW, we have the higher than the leveling in the vertical accuracy, 0.1 to 0.5 centimeter. And the next one, INSA, they have the good spatial resolution. However, in this study, because I want to understand the mechanism, I don't want to investigate for more region, so I want to understand the mechanism first. So I just use the leveling, continuous GBS, and MLCW to explore the mechanism. Here, we can see the observation data of the groundwater and the rainfall data. We can see in the dry season, they decline due to the discharge. And in the wet season, they will recover. You can look at very stable in the wet season and dry season during 10 years from 2007 and 2016. They quite stabilized. However, if you look at the land subsidence, they continue decline. The red line is the GPS data. The black line is the MLCW data. You can see if the groundwater is stabilized, why we have the continued decline. They have the, maybe due to some mechanism, we don't know. So we have the increase of groundwater level, the subsidence can be recovered. The decrease of groundwater level, they will subside. However, they cannot reach the original. So another one, why we have the difference between the surface total subsidence and also the shallow one. It means they have some hint. The subsidence in a deep depth larger than in a shallow depth within 200 meters. They have the meaning here. So this is the symbol illustration for you to the first GPS, INSA, and leveling measure in the ground surface. The next one, MLCW monitoring in the unconsolidated sediment, maybe 200 or 300 meters. In this study, 200 meters. And the shallow compaction in 200 meters can be due to surface loading here, the houses, and also the groundwater over ejection here. Also the natural compaction or the factor, a lot of factor, we don't know. Another is tectonic subsidence, because in Pingtung Plain have the subduction zone. So they have the erosion plate subduct to the sediment sea plate. So they continue that. And the total subsidence will be simplified to the subsidence due to the groundwater ejection and natural compaction and tectonic subsidence. So another author point out the S-wave velocity in this area very shallow, around just the limit of the unconsolidated alluvial sediment, just around 200 meters. You can take a look. The 0.2 to 0.5 kilometers per second, the velocity, the S-wave velocity here, just 100 meters, 200 meters, and they will become the lighter. So it means more deeper, the sediment will become more solid or more consolidated, something like that. So based on the geological point of view, the first, more deeper, they more cemented or partial cemented media. The next one, during the just only here, we just use the data just 10 years. If we compare to the long scale of million years of the geology, so the natural compaction is not totally obvious here in this study. So I try to make assumption the natural compaction here in this study, in this area, can be ignored first. And the simplified tectonic subsidence can be the total subsidence minus the subsidence due to the pumping. It means the total one minus the shallow one, we can estimate the deeper one. So we can do the time series analysis with the Pearson correlation, just have the positive correlation or the negative correlation, because they can say that about a high correlation or low correlation can have the good discharge or good recharge, something like that. And this is a result and discussion. In the seasonal deformation, we can see if we have the dry season, the deformation rate is the negative. The negative is the compaction. And in the wet season, they have the expansion here, the positive value. They have the expansion. However, the wet season, on average, just around 52 millimeters per year. However, in the dry season, it's more larger. If we compare the line here, it's on way below the zero. It means they continue subside and they have the residual subsidence. It means they cannot totally recover. It means they subside a lot and recover a little bit, and subside a lot and recover a little bit. So maybe this delay behavior in the shallow one, or tectonic. So this is the correlation matrix between the MLCW data and the groundwater data here, and also the Jiatong area and also Fanglao area. We can see they have the good correlation of about 0.6 to 0.9, and then we can say that MLCW in the vertical deformation can be used to detect the land subsidence due to the groundwater variation in the shallow depth within the 200 meters. And how about the difference between the area? Because these two areas very close, so the R value, the correlation is quite strong. It means they pumping together. It means due to the decision they need to fish. They have the fish pond there. They need to fish the fish, so they need to pump the water, so they can have the quite similar behavior. So see that it means the seasonal effect in this area and also the pumping behavior quite similar in these two areas. So the tectonic deformation and estimation. The red line is the GPS data, and the black line is the MLCW data. So we see the difference between them, and then I make the easy symbol about the result of tectonic subsidence equal to GPS data minus the MLCW data, and then I can estimate the subsidence. The subsidence here is we can see it's large, around 5 centimeters, accumulate through 10 years. It means below the 200 meters, they have the subsidence. So we think this is due to the tectonic. Because in the previous slide, I mentioned that below the unconsolidated sediment is quite shallow, around 200 meters around, because the S-wave velocity show that. So we think maybe due to the tectonic with the trend line. And here we also analyze about the horizontal movement from the GPS data. We can see they move to the azimuth here with the horizontal deformation around 27 millimeters per year among 10-year period. So they move to the southwest. Why they need to move to the southwest? So the question is coming. Here, this is the diagram to show you, because in this area have the tectonic activity, very active. When the Philippine Sea Plate come to Taiwan, they will make the central range more up, because they have the intrusion. So the Pingtung Plain will carry the stress. So if you carry a lot of stress, so where you need to release the stress to make your balance, something like that. So where they can escape, the free boundary. The free boundary in the sea, Taiwan Strait, they have the free boundary here. They have the tectonic escape. This is and our result consistent with the previous study. They move to the southwest, and here also move to the southwest. So we can know that a current tectonic escape with the transitional deformation to release the stress caused by the Philippine Sea Plate to make don't have the they can release the jet, yeah. And the tectonic subsidence associated with the tectonic intrusion in the southern tip of the Taiwan collection belt. From some author already figured out that, when we totally agree that, because our results consistent. Okay, and now we can draw the conclusions. The first, the land subsidence in Pingtung Plain. What's the reason? The first, human impact. We quantified around 82%, but this is the previous slide during 3 years ago. So recently we try to do more, and we have an update. So, and then we quantify around 82% due to the human impact in this area. And because the MLCW device can detect the land subsidence due to the pumping within the 200 meters in this area, and also the discharge and recharge period, by using the fast-word analysis, we can know that around 1 year interval, they match the hydrogeological condition. And the second one, natural impact, around 28%, and natural combustion ignored first. And we just focus on the tectonic escape to the southwest direction, and we generally agree that the regional subsidence due to the tectonic. However, the local subsidence may be due to the pumping, because the scale here is different. This is also the weakness in this study, because commonly in the groundwater management, they know about the region just several hundred meters, around 300 meters or 200 meters. However, in the tectonic or geological point of view, they focus on the kilometer scale, around 1 kilometer, 2 kilometers. So we have some weakness in here. However, we try to overcome this challenge. Yeah, this is our team member, and also have some activity for the student in Taiwan. Yeah, this is my advisor, the blue here. Yeah, thank you very much.
Thanks a lot. Questions? Yes.
Yeah, you mentioned the tectonic subsidence is about 28%. It seems very reasonable for me. So what is the rate, average rate of a tectonic subsidence?
You mean what is the reason tectonic?
No, what is the rate? How many millimeters per year for the tectonic one?
Around, if we consider 10 years, around 5 millimeters per year.
So 5 millimeters per year.
Yes.
I believe that the people study geology or tectonics, they already did something, but long term about the average rate of subduction. So what is the number that they gave?
Pardon?
Because tectonic subsidence rate, that's a subduction rate.
Yes.
Yeah, so what do you find? I forgot, I don't know, but I believe they have a publication about the subduction rate.
Because I just read some publication before, they also mentioned about that. And then we try to investigate the mechanism here. And then we think not on also the tectonic here is active, but if we don't care about the tectonic activity, so what's another mechanism here? Yeah, so yes.
Age. But the two numbers should be comparable, because tectonic subsidence, that rate should be constant.
Yeah, because at the beginning we put a question mark maybe due to the deep pumping, but the deep pumping in here is they are very solid.
No, you are right.
Yeah,
you are very right.
No, we don't have an independent.
No, you are very right. What I want to say is that we need to figure, because you didn't give the number, you just say, okay, 28%.
Yes.
Yeah, you 28% of total subsidence. Yeah, what I want to know is what is that 28%? So for example, you may say, oh, 3 millimeters per year, 4 millimeters per year, something like this. So I want to get this number.
Okay.
A great job.
Okay. Yeah, around.
You look at the total rate, and then this 28%. How much millimeters per year would that be? You looked at that?
Okay, maybe 5. Yeah. Because I analyzed it around 5 millimeters per year.
There you go.
You just say that this tectonic part takes 5 millimeters per year, and this is also what the graph show, because those displacement occur over 10 years, so it's about that 5 centimeter over 10 years, more or less. This is what one of the graphs shows. So 5 millimeters per year seems due to this.
I'm happy we have a room full of scientists that we figured this out. Last question. Of course, on the other side.
Thank you very much. Very nice presentation. I just wonder, the conclusion you said that the tectonic straits flow to the southwest direction. How do you get that conclusion?
Because I analyzed the GPS data. Because GPS data, they have a three-dimensional. So I can combine the S and Y, and then I can compute the horizontal deformation and also their vector. And then I can know that they have the the azimuth here, because the north direction is here, and then now they move to here. So they have consistent in the southwest direction.
Okay, see.
Yeah.
But for land subsidence, it's not only vertical, it can also be horizontal.
Yes.
So that GPS results, maybe that deformation horizontal maybe should include the deformation caused by groundwater pumping, not only tectonic.
Yes.
Yeah.
Yeah,
That's-
because the GPS data is the total. They are total subsidence because
Yeah.
they measure in the round surface. It means the shallow one including with the deep one. This is the movement, the displacement. It's moving up, moving down, something like that.
Okay.
Yeah, thank you.
Okay, thanks a lot, and
Yeah.
thank you again for your
Thank you very much.
presentation.